One of the ways that we track what's going on in a reaction is by looking at temperature changes. When we look at this, we have some values that help us understand what's happening to our system and what's happening to our surroundings. And one of the things that we look at is this thing called the specific heat. When we look at the specific heat, we are considering basically the capacity of an object to absorb energy. Okay? And so we've got the heat capacity. We can look at the heat capacity in terms of Kelvin, the amount of heat required to change the temperature by 1 Kelvin. Now, what's better though is the specific heat capacity. We're looking at how much heat it takes to raise 1 gram of substance by 1 degree. Now, there is something interesting here. I've got 1 Kelvin here, but I just said 1 degree. Well, when we talk about Kelvin, we don't use degrees. Degrees are for Celsius. So think about Kelvin and Celsius for a moment here. Put that in the back of your head. We can also talk about the molar heat capacity in terms of joules per mole Kelvin. Usually when we're dealing with heat capacity, though, we're thinking about specific heat capacity, and that's the joules per gram Kelvin, or joules per gram degree Celsius, as you'll see on the next slide. The numbers are the same, though. So again, think about this for a second. All right, so we've got our specific heat capacity, and here are some substances with their specific heats. Now, this is an intensive property. And I can also put this in terms of joules per gram Kelvin. Okay, but the numbers are exactly the same. So if you look here, I've got delta T, right? So that's the change in temperature. Now, when we think about Kelvin versus Celsius, what goes on between Kelvin and Celsius? Well, they're just an additive difference. If I have 0 degrees Celsius, I have 273.15 Kelvin. If I have 100 degrees Celsius, I have 373.15 Kelvin. Well, what's my delta T in both of those? 373 minus 273 is 100. 100 minus 0 is also 100. And so the delta T does not change between Celsius and Kelvin. If something changes by 5 degrees Celsius, it also changes by 5 Kelvin. All right, and so you're going to see the specific heat capacities depending on where you get the numbers from. Sometimes you're going to see them in joules per gram degree Celsius. Sometimes you're going to see in joules per gram Kelvin. The numbers are exactly the same. Okay? So, if I have an unknown object and I know a bunch of heat capacities, can I figure out what the object is if I can figure out the heat capacity of my object? Yeah, because it's an intensive property. Okay, now let's take a look here. I've got aluminum, I've got copper, and I've got water. Which one has the highest heat capacity? Water does. All right, so it's going to take more heat to warm 1 gram of water by 1 degree than copper or aluminum. And this is actually really, really important. If our bodies weren't mostly made of water, we would be much more temperature sensitive than we are. But because we're mostly made of water and it takes a lot of energy to raise 1 gram of water by 1 degree, it's a slower change, either heating up or cooling down. If you have a pool or access to a pool, you'll notice that once the weather starts to warm up, that pool is still pretty cold. It takes a long time for a pool full of water to warm up when the temperature warms up outside. And so the oceans are a great heat sink because of this really high specific heat capacity. Okay? All right, now when we look at things though, when we do calculations, we don't usually measure the specific heat capacity and then back calculate the heat. I mean, sometimes we know it and we can back calculate the heat, but a lot of times if I'm doing an experiment, what can I measure easily? Well, I can measure the heat, okay? Or I can measure the change in temperature. Or if I know the specific heat capacity and I know the mass, then I can calculate the heat. And so we have this equation here. It's Q equals mc delta T, okay? And a lot of people call it the MCAT equation because the delta looks like an A. But here we've got the mass of whatever we're doing, the specific heat capacity, and then the change in temperature equals the overall heat involved in our reaction. Okay, and again, the delta T, it's a change, and so the Kelvin or Celsius actually doesn't matter because you get the same degree of change because the degree size is the same. Okay, and so remember, first law of thermodynamics, energy is neither created nor destroyed. So whatever sign one has, the surroundings have the opposite sign. Okay? So how do we do these sorts of experiments? Well, we look at something called calorimetry. Now, there's two types of calorimetry that we can do. There is the classic coffee cup calorimetry. So this is a coffee cup calorimeter. Okay, and what is a coffee cup calorimeter? Well, we want to try to keep everything as insulated as possible so that we can track these changes. And so we use something that's insulating. Styrofoam is fairly insulating. And so usually a classic coffee cup calorimeter is two styrofoam coffee cups just nestled in each other with a lid on top. Okay, and so I've got, my sample and my calorimeter. So usually what's happening here, okay, is in my coffee cup calorimeter, I have water. Okay, and so I get the initial temperature of my water. I heat an object up, I get the heat of my object, and then I drop that object into the water. My object is going to cool down, and so it will get a negative Q. My water inside the calorimeter will heat up, so it gets the positive Q, because the heat gained by water is going to equal the heat lost by sample. Now, this is usually done with metals because if I drop a metal in water, is it going to dissolve? No, it's not. And so we need something that I can, you can drop in water without it dissolving or disintegrating or anything like that. And so Q is equal to MC delta T, so I get mass times heat capacity times change in temperature. Mass times heat capacity times change in temperature. All right. Now, for these, we use water a lot, and so the specific heat of water, again, is at 4.184 joules per gram degree Celsius. We're going to use that quite a bit when we look at experiments like this. Okay. All right, so here's an example. I've got a metal. It's heating in boiling water, gets up to almost 100 degrees. It gets dropped into an insulated system with an amount of water at a certain temperature. Okay, and then my water and my metal come to a final temperature together. What we don't know is the specific heat of that metal. So we're going to try to calculate the specific heat of our metal. And so the heat of our water okay. All right. So let's take a look at the variables we have. So we know a couple of different things. I've got my water. All right. So I have 225 mils of water times 1 gram per mil. So I have 225 grams of water. Okay. Specific heat capacity is at 4.184 joules per gram degree Celsius. And then delta T, the final temperature that the system came to was 23.1 degrees Celsius. The initial temperature of the water was 21 degrees Celsius. So I'm going to get 2.1 degrees Celsius. Okay. Now my metal. All right, our problem tells us that the mass of the metal was 55 grams. The heat capacity is what we're trying to find. Delta T. Again, the metal got dropped into the water. All right, so the metal and the water are both at the same final temperature. So we get 23.1 is that final temperature. The metal started off at 99.8. And so the change in temperature there was negative 76.7. Okay? All right, and so remember, Q is equal to that MC delta T. Okay, so for my water, I have 225 grams times my 4.184 joules per gram degrees Celsius times my 2.1 degrees Celsius equal to negative 55 grams, unknown heat capacity, negative 76.7 degrees Celsius. Okay, so that negative sign is very important because if the specific heat capacity is the amount of energy required to raise 1 gram of a substance by 1 degree, can I get a negative heat capacity? No. And what happens to the metal? Well, it's losing energy. It's losing heat. And so its delta T is negative. Well, I've got a negative over here and then a negative temperature. Does the negative cancel out the negative? It does. And so we end up with this positive heat capacity. Okay, and so this is just basic algebra. Combine your like terms. We solve for C. We're going to get 0.47 joules per gram degrees Celsius. Now, if we had a set of data in front of us, we would be able to figure out what the identity of that metal is. But I don't have a whole bunch of metals printed on a slide, but because it's an intensive property. So we can use specific heat capacity to identify the metal. All right, so there is the heat capacity of that metal. All right, now, this is a crazy one. I'm going to have an alloy of 2 metals. So I've got a sample of copper and aluminum heated up to a certain temperature, put into a calorimeter, all right, and we had a temperature change. So we're assuming that no heat was lost to the surroundings. We want to know what the mass of each metal in the sample was. We've got the specific heat capacities of both copper and aluminum here. Okay, so we know a few things. We know that the mass of the metal is going to be equal to the mass of copper plus the mass of aluminum, and that is the 33.14 grams, okay? I can rearrange and I can get the mass of copper is equal to 33.14 minus mass of aluminum. That way I can solve for one variable and plug in, okay? So when we look at this, all right, we can look also at what's happening to our water. So heat, because this will make the equation less clunky. If I have an MC delta T and then my system, or then my 2 variables over here. So my heat gained by water okay, is again going to be that MC delta T. All right, so we had 250 grams, 4.184 joules per gram degrees Celsius, and then 23.05 degrees Celsius minus 21. So 2,144 joules is how much heat the water gained. So that's how much heat the metal lost, okay? So our heat lost by metal is going to be that 2,144 joules, but we need to figure out some masses of our metals, right? And so if I have an MC delta T plus an MC delta T, okay, I can distribute that delta T and I can do the MC plus the MC quantity times the delta T. So it looks like this. Again, that's algebra. So If you're taking this level of a course, we do expect that you have taken algebra and understand the distributive property. All right, and so I get that delta T, and so I get the mass of my copper times the specific heat capacity, 0.385, plus the mass of my aluminum times the specific heat, which is 0.902. Okay, and so it looks like that. Okay, because again, what I'm doing is an MC delta T plus an MC delta T. Okay, if the delta T is the same, okay, then I can do this as MC plus MC times quantity, or quantity times delta T. Okay, so that's all I did there. Just that distributive property, because the delta T is the same, because it's the same piece of metal, because it's an alloy together. Okay, all right, so we've got some information. We know the masses of, our metals are represented by M. We know the total mass of our alloy, and so we did that substitution. And so now we can plug this all in. We can also get the delta T. So this delta T, we're looking at 23.05 minus the 119.25, and so this delta T is negative 96.20. Okay, so now I can plug in and we can solve. So 2144. I'm going to strip all of the units out of this just because otherwise I don't have enough space to write it all. So I'm going to strip the units out as I write this out. So there's that delta T. There's the mass of my copper. There's the specific heat of my copper. There's the mass of my aluminum and the specific heat of my aluminum. Okay. All right. And then it's just a matter of doing algebra to solve for the mass of aluminum. Okay, and so when you do algebra, you're going to get the mass of aluminum is equal to 18.43 grams. The mass of the copper is the 33.14 grams minus the 18.43 grams, and you're going to get 14.71 grams of the copper. Okay, so we can put it all together like that. All right, now there's another type of calorimetry. What if I want to know information about something that I can't like heat up and then drop in water? Like what if I want to know, I don't know, the amount of energy in a piece of celery? Can I heat that up easily and drop it into a coffee cup calorimeter? What if I want to know the amount of energy in a Dorito? We get all mushy gunk, right, if I tried to heat it up in water. So that brings us to our second type of calorimeter. This is called a bomb calorimeter, okay? This is a bomb calorimeter. So in a bomb calorimeter, what's happening is we have a system where there's a little chamber, and in that chamber, we combust our sample. And as we combust our sample, it gives off energy. And then there's water around it. And so then the water heats up. And so we can figure out how much energy the water absorbed when we combusted our sample. Now, when we do this, the calorimeter itself is going to have a heat capacity. And so the amount of energy lost by our sample is going to be equal to the amount of energy gained by both the calorimeter and the water together. And we can do a modified version of this where we don't necessarily combust it. We can have a type of this where we do have it like an insulated thing like in styrofoam cups even, where we do a reaction. If I'm reacting two chemicals together, I'm not going to heat one up and drop it into water. I'm going to do my reaction, all right? And so it's the same situation where I have to get the specific heat capacity of my calorimeter, all right? And then when I do the reaction, I gauge how much energy was given off by my reaction, and then I can get that information. And so, the Q of my water is still going to be MC delta T. The Q of my calorimeter, the heat of the calorimeter, is just going to be the heat capacity of the calorimeter itself times the change in temperature of the whole system. Okay? So let's take a look here. So I've got octane, it's in gasoline. We've got a sample that is burned in a calorimeter that contains a bunch of water. All right? And so what we need to do is we need to figure out how much octane, or how much energy from the octane. Now, one thing that you're going to see that's going to be really weird with a lot of these is we'll practice a few different ways, but usually what we're looking at is we try to figure out how much energy is given off, per mole. And so sometimes when we balance these things, we get some really, really weird balances where we don't want to put a 2 in front of the component that we're looking at. And so things get balanced kind of strangely with halves, because a traditional balance of this, if I put like a 9 here, okay, that's cutting the hydrogen in half over there. Well, that would end up giving me an odd number of oxygens, which I really can't do if I have O2, right? But let's see here. If I put a 9 there and an 8 there, okay, 8 times 2 is 16, all right? And then 16 plus 9 is 25. So I'm going to balance this with 25 halves O2. It's a little bit weird, right? But that's because I want to keep a number 1 there, all right? I want to figure out how much this is going to burn off per mole. And then we have a 1 gram sample, so we'll have to do some stoichiometry at the end. But a lot of this stuff, a lot of the tabulated data we have is done per mole. And so we do end up a lot of times with these weird half balancing. So we don't normally do that, but we do it for our thermo stuff. Okay, so the heat of our reaction is going to equal to the heat of our calorimeter plus the heat of the water. Okay? All right, so remember the heat of reaction, it's giving off energy. Okay? And so negative Q reaction is going to be, so we had some information. We have a heat capacity of the calorimeter, which was 837 joules per degree Celsius. The change in temperature was 8.2. You can go back and calculate that if you want. All right, and then our water, we had 1,200 grams, 4.184 joules per gram degree Celsius. And we also had the same 8.2 degrees Celsius. When you do these bomb calorimeter problems, the delta T is the same for the calorimeter as it is for the water because it's all being done in the same thing. All right, so when we do math, we get 48,033 joules. Okay? Now, we want to calculate the molar heat of reaction. Okay, and so we balance that to that 1 mole, right? So, molar heat of reaction, or actually, I'll put it over here. So, delta H of reaction, that's what we're doing with our molar heat of reaction, is usually in kilojoules per mole. Okay? And so I need to convert this joules to kilojoules. So I'm going to get 48.033 kilojoules. All right, now I have this negative Q of reaction. And so I'm going to do Q of reaction is negative 48 0.033 kilojoules. Okay? All right. So now I need to get to kilojoules per mole. So I had negative 48.033 kilojoules of energy for that 1 gram of octane. I need kilojoules per mole, so I just need to do a grams to mole conversion. It's 114 grams for every 1 mole. And so we're going to get negative 5,500 kilojoules per mole, because our 1 gram gave off our 48 kilojoules, and when we do our conversions, we get 5,500 kilojoules per mole. And that is how we deal with our heat when we're looking at our calorimetry problems.